capacitor had like some sort of glass in between the plates, then it wouldn't be so simple. And basically, if you put in some sort of like other material in here in between the two plates, this material right here was called a dielectric. And then that would tweak the formula. And instead of just looking like, oh, the capacitance equals epsilon 0 times A over D, you would also have to put in a little K right here. And that was called the dielectric constant. No, that's not the same K. All right, well then let's call it, I don't know, weird K, but that's not the same K, and I'm so glad you point that out. I didn't even think about making note of that. Thank you. Okay, that's a different K. That's a dielectric constant K, and that depends on the material. Like, glass has its own K value, plastic has its own K value, any kind of material that you put in there. Well, it increases the capacitance, and it enables more charge to be held on there. My point is, if there isn't any material in there, then K is just 1, and you're left with the permittivity of free space, epsilon 0. Now, you might say, hey, why am I bringing this up now? We're not even really studying capacitors right now. Well, the reason I'm bringing this up is when we study the electric field around the charge, we're basically studying it as if it's in empty space, as if it's in free space. And there's another way of writing this K constant, which is not the same as the dielectric K constant. This K constant can be written in terms of epsilon 0, the permittivity of free space. That's right, ladies and gentlemen. So a more sophisticated way of writing this formula is to replace K, I'll write this in black here, the electrostatic K right here, this one right here, the universal electrostatic constant K, we can replace that with 1 over 4 pi epsilon 0. Now, I'm not going to get into the proof of why K equals 1 over 4 pi epsilon 0. All I'm telling you is, just like over here, when the only thing in between the capacitors was empty space, well, we had that epsilon 0 right here. Well, when the only thing surrounding this charge right here, we could write this in terms of epsilon 0. So we could write Coulomb's law as F equals K Q1 Q2 over R squared, or what's the new, cooler, more sophisticated way of writing it? Yeah. 1 over 4 pi epsilon 0 times Q1 Q2 over R squared. And of course, if you want to know what the value is of epsilon 0, you could just use this value, 9 times 10 to the 9th, and solve for it. And another way of writing this electric field strength formula right here is the electric field strength formula equals 1 over 4 pi epsilon 0 times Q1 over R squared. Thank you very much. Oh, thank you very much, people. Thank you. So, what's that? It's a common practice, and if the charge wasn't placed in the free space, we'd have to introduce a dielectric constant. So this is a more sophisticated way of stating those two formulas. It's 6 in one, half a dozen in the other. You guys want to be just as comfortable writing it with the K or writing it with 1 over 4 pi epsilon 0. We're not even going to get into that. We're not even going to get into that because we're never even going to be studying that. I just want to show you the relationship between this epsilon 0 and where else we see it. All right. So we now know, hey, at this particular point right here, if you want to know the strength of the electric field, well, the strength of that electric field is equal to 1 over 4 pi epsilon 0 times, Q1 over R squared. Woohoo, Jiffy-Loo! So this is where we're starting. This is our groundwork, people. You want to be very comfortable with this because we're going to, this is the basics. This is like 2 plus 2 equals 4, and now we're going to learn how to do 67 plus 28. You know what I mean? This is the basics. Okay? So now that we have this done, what we're going to do next is we're going to figure out the electric field in all these scenarios here. Let's say you have a charged rod and you have a point right next to it, like right over here. We're going to have to calculate how strong is the invisible electric field there. We're also going to have to figure out if you had a curved rod in a semicircle. Let's say this rod was positively charged. We're going to calculate the strength of the electric field right at that center point of the semicircle. One of the hardest ones to figure out is this one here. If you have a charged rod, like a positively charged rod, and you have a point right next to it, right here, we want to calculate the strength of the invisible electric field. Two more. If you have a ring which is positively charged, and here's an axis coming through the center. So this is like a three-dimensional drawing here. It's like if this is the tire, the tire's like this, and I have the axle coming out right here. Well, we want to be able to calculate how strong is the invisible electric field right there. And last but not least, if this isn't just a little ring, but if it's a solid disc. So we have a disc like this, and the whole disc is positively charged. Again, coming straight out, an axis right over here. At this point right here, we want to calculate the strength of the invisible electric field.
How is that different from the original one, where it's just like the capacity term? See, I know it's a circle instead of a square, but for a metal plate.
Well, eventually we are going to do the electric field for a capacitor. After we do that, we are going to calculate it. And there is a slight difference. Now, this guy here, this is like the 2 plus 2 case. This is the basics, yes? And we know this is the basics right here. Well, this is going to be the root that we always start off with in all these cases here. But guess what we're going to have to do? Calculus. We're going to have to use calculus in all of these cases to figure out the electric field strength. Now, the bottom line is, people, if you could do these 5 problems, if you could do the calculus of these 5 problems, you could do the calculus needed for the rest of the year. Like, I'm sure there's going to be other things that come up. Don't get me wrong. But, like, if you could have a gut understanding of how to do the calculus for these 5 cases right here, then you'll be able to figure out and have a gut understanding of all the calculus that's going to come henceforward. And it's always going to boil down to, well, we're going to break it down and we're going to look at a little tiny piece here, a little tiny piece of that charge on the rod, and guess what we're going to call that? DQ. A little piece of charge, DQ. And over here, there's going to be, and that's kind of like a point charge. Yes, that's kind of like a little point charge. And then over here, there's going to be an electric field just due to that little piece of charge right there. And guess what? Guess what the electric field strength is, due to the little DQ? DE. A little piece of the electric field strength. So we're always going to break it down into a little DQ and a DE. So that's our quest, and that's where we're going.